Splitting. So this is proton NMR. It's the fourth thing that proton NMR tells us, and it's what makes it such a powerful technique. The splitting pattern tells us about the hydrogens on the next door carbons. So very, very powerful because it tells us what's either side of us to some extent. An important point, OH hydrogens don't get split or cause splitting. So no splitting of an OH hydrogen, and they don't cause any splitting either. There's a table that you just need to memorise really, and if you practice using it you will memorise it quite quickly. So the number of hydrogens on the next door carbon, and then the splitting. It's an easy pattern to learn. If there are no hydrogens on the next door carbon, there is no splitting. So what you see is just a line which we call a singlet. If there's one hydrogen on the next door carbon, you get splitting into two lines, which we call a doublet. If there are two hydrogens on the next door carbon, the line splits into three, which we call a triplet. If it's three hydrogens, then it splits into, can you see the pattern? Four, which this time we call a quartet. If it's four, then it splits into five. If it's five, it splits into six, and so on. We kind of have a bit of a cop-out and we just call it a multiplet once it's above a quartet. They have proper names, but we don't need to know them. So learn that pattern. Count how many hydrogens you've got on the next door carbon, and then add one, and that's your splitting pattern. The peaks split in a particular way. It's Pascal's triangle, but you don't need to know that. You can look up a bit more if you're interested. Let's do an example. Let's do a nice straightforward one. Okay, remember we've got three hydrogen environments. Therefore, we would see three peaks, and the ratio would be 3 to 2 to 1. This is an OH hydrogen, so they don't cause splitting, they don't get split. So this would appear as a singlet, just one peak. If I look at these hydrogens, there's only one carbon next door. There are three hydrogens on that carbon, so I add one, and this therefore would be a quartet. So it's a peak of an area or a ratio or a height of 2 that is split into a quartet. And it's split into a quartet because we say it's coupled to, i.e. it's next door to a CH3. So it's a coupled to a CH3. This peak, which would have an area or ratio of 3, is next to a carbon with 2 hydrogens, so we add one, and this would be a triplet because it's coupled to a CH2. So your spectrum would have a singlet, a quartet, and a triplet, and that helps us to build up a picture of our molecule. Let's have a look at another one. again. 1, 2, 3 hydrogen environments, therefore 3 peaks. The ratio of 3 to 2 to 2. If I start here, these 2 hydrogens are on a carbon which is next door to a CH2. Therefore, this would be a triplet. It's coupled to a CH2. These ones, I need to look on both sides. So this side, my carbon's got 2 hydrogens, and this side, my carbon has got 3 hydrogens. So in total, there are 5 hydrogens next door. So therefore, it would split into 6, but I can kind of cop out and just say that would be a multiplet. Here, I've got 3 hydrogens, which are next door to a CH2. So I would say they're coupled to a CH2. So this would be a triplet. Look very carefully when you're looking at what's next door, particularly sometimes if you've got a C double bond O or a kind of something like that, it might trick you. But remember, look on both sides, count up how many hydrogens you've got on the carbons which are next door, and then add 1 to give you your splitting pattern. Hope that helps.